Okay, so we're going to start off with cross products, and then we're going to talk about angular momentum, and then finish up with, if we have time, the static equilibrium problem. We didn't get a chance to do enough practice on those last time. We ran out of time. Okay, so we already did cross products, but we're going to introduce another formula, but I like to review the whole thing again. So cross products of vectors. Okay, so we have a vector A cross B. Okay, so let's say A is like this. Let's say it's in the plane of my sheet of paper, and B is in the plane of my sheet of paper. So A cross B is a vector with magnitude and so I'll just write this. A cross B magnitude is equal to the magnitude of A times the magnitude of B times, if this is the angle, let's call it phi, sine of phi. Okay. Now, the other point is that the direction of A cross B is given by the right hand, what I call it, sorry, the cross product right hand rule. Okay, so the first part of the cross product right hand rule is that the cross product is perpendicular to both vectors. Okay, so in particular, these two vectors are in the same sheet of paper, is on the sheet of paper or on the screen, and so therefore the cross product is going to be perpendicular to both of them. Either they come out at you like this, or they go into the page like this. And determining which one it is given by the cross product right hand rule. Okay, so if I draw a three-dimensional perspective like this, so A and B are in this, on this plane drawn as a three-dimensional perspective, then it's actually this vector is the direction of A cross B. All right? So do you remember the cross product right-hand rule? That was in one of the videos from last week. Remember that? Okay? So what you do is you put your fingers, let's do it with this one here. Everybody put up your right hand. All right? Stick your fingers like little arrows, okay? Stick your fingers in the direction of the first vector. Okay, A is going down a little bit like this. Okay, so you're pointing in this direction. Now, the whole trick of the cross product right hand rule is about the fact that your fingers only go one way. They don't go the other way. Okay. So now what you do is you rotate your wrist so that you can flip from the first vector to the second vector. So I have to rotate my wrist so that I can flip from A to B. Does that make sense? Because if my wrist is in this position, I can't flip from A to B. So if I do this way, I'm flapping in the wrong direction. So I need to go from A to B this way. Okay. Once you've done that, you close your fist and you stick out your thumb. That's the direction of the cross product. Does that make sense? Okay. I'm not going to write that out. It's in my notes. It takes like 3 minutes to write all that stuff out. You just put your fingers in the direction of the first vector, and then you rotate your wrist so that you can flip to B. So I have to rotate my wrist, so now I can flip to B. A to B, A to B, A to B, okay? Then you stick out your thumb. You close your fist, stick out your thumb. That's the way it goes. All right, questions about this? All right, good. Now, the reason I'm reviewing this, so in principle, you already learned this. We're now going to write down the cross product rule in terms of components. So how many of you actually know this, how to get the cross product of two vectors with components? Okay, so this is probably new to most of you. Now there is a formula, if you've learned this before, where you take the determinant of a 3x3 matrix with I, j's, and k's, but I've learned that, having taught this class quite a few times, even if you've learned that formula, if you had to bet your life on whether you could do that formula without making a mistake, most people would say no. Okay. So I'm going to show you a simpler way to do this, right? That makes it a little easier. So this, I actually made this up for a class like this at NC State, and students seem to like it. Okay, so we write down a vector. So we want to do A cross B, all right? This is what we're after. And we want it in terms of components. So let me start a new sheet of paper. All right, so we have vector A. It has components AX, AY, AZ. Then we have a vector B, which has components BX, BY, BZ. Okay? The first thing you do is you just make a table of these things that I've drawn out, where the first vector is on top. So first, this guy's the first vector, this is the second vector. A is first, B is second. Okay. You just make your table. You write AX, AY, AZ on top, BX, BY, BZ on the bottom row. Okay. Let's call the vector C A cross B so that it has a simple name to it. So we don't have to keep saying A cross B. Okay. We're going to get the components of C one by one. Okay. First, we're going to get the X component of C. All right. The way you get the X component of C, so we're going to just draw this table several times. So we first take the table. Let's do it again so I don't screw up the original one I've drawn here. And because I want the X component, what you do is you cross out the X column. Right? And what I'm going to call the diagonal is going like this. Okay? Going from AY times BZ. So it's a product of these diagonals. So how many of you are familiar with matrices? Matrices. Okay. So these are what are called the diagonal elements of the matrix. A matrix is just a table, a square table of numbers. And these guys are the things along the diagonals. So what you do is you multiply these two together. The order doesn't matter, but I'll do it in the same order each time so that you have a consistent formula. So you do AY times BZ. So there's a product between the two. Okay? Everybody good on that? Okay? And then these are what are called the off diagonals. These guys here. I'm going to multiply these together, but I'm going to subtract the product of those, AZ minus BY. Okay. And that is the formula for CX. This is actually on your equation sheet, but so you can just look. You can look up this formula on your equation sheet, but I think it's a little bit easier to do this way. Okay. So next, I'm going to do CZ because I'm going to skip CY for just a moment. CZ is just as easy. But any questions on CX? Everybody got that? Just multiply these things going from left to right down, and then the other way, the off diagonals with a minus sign. Okay, now I'm going to do AX, AY, AZ. Again, copy BX, BY, BZ. And now to get the Z component of C, cross product, you do this the analogous thing. You cross out the Z row because of the Z column because I want to get the Z component. Okay? And now what you do is you do the same thing. You multiply these guys, which are called the diagonals. So you do AX times BY. Right, the diagonals. And then you subtract the product of the other two, the off diagonals, AY minus BX. So that's the formula for CZ. Okay. Questions about that? Yeah. The order of subtraction absolutely does matter. The order of the product doesn't matter. So you can write, I could write this as BY times AX. It doesn't matter. Oh no, okay. The vector cross product, the order does matter. So if you do A cross B, and you switch the order to B cross A, you will get a minus sign as a result. Okay. It was just simply inside here the order didn't matter. Okay. Other questions? Does everybody follow this for CX, CV? All right. And then if you want to get CY, CY is a little slightly more complicated one. There's an extra step for that. What you do is you cross out, because you want the y component, you cross out the y column. Okay? But now this guy, this column, there's a gap between the two. So what you do, the trick is you take this guy and move it over, bring it to the other side. You wrap it around. Okay? You bring these guys over here. So now that you have another 2x2 block. Okay? If you wanted to take this guy and wrap it around the other side, that works as well, but most people find it easier to go forwards like this. Okay? It gives the same answer. And now then what you do is you take the product of the diagonals, same formula. You go AZ times BX minus the product of the off diagonals minus AX BZ. And that's the formula for CY. Okay? Any questions about that? Okay, so my experience is doing it this way. You just draw these tables. It's about the fastest way you can get the cross product components. We'll do examples when we do some practice problems. Okay? It's also, these formulas are also on your equation sheet, so you can just read them off if you want. But typically making these tables is a little bit nicer. Any questions? All right, I did want to review these directions though, about the spin. Remember, there was another right-hand rule, so since we're doing right-hand rules, so remember, I have this other thing called the spin around right-hand rule. And these terms, cross product right-hand rule, spin around right-hand rule, these are not standard. So if you are at work someday and you talk about right-hand rule, typically people only talk about one right-hand rule. But I made these different names because students in the class very similar to this complained that the right-hand rule was being used in different ways, but they were always called the right-hand rule, so it was really confusing. So I made up these names. One was the cross product right-hand rule, where you put your fingers in the direction of the first vector, you turn the wrist so that you flip to the second vector, you stick up your thumb, that's the direction of the cross product. Now this is a spin around right-hand rule, which is very simply, if you have something that's spinning like this, okay, what you do is you think of your fingers of your hand as little vectors, the tips of the hand as little vectors, and you cup your fingers so that it's going in the direction of the rotation. So this is, right, the same way as the wheel is rotating. Really fun. Fingers in my hand. Then you close your fingers and stick at your thumb. That's the direction in which we talk about the rotation of this little wheel. Okay? So we're going to talk about the angular velocity as being a vector for this direction. So if I would go the other way, right? If I go now if I wanted to go the other way, then I need to cup around and go like this, right? So then I stick up my thumb, it's going in this direction. Yeah. So notice that it's going like this, right? So I'm cupping my fingers in this direction. You see how my fingers are going the same way? Like this? Like this? Right? I stick up my thumb, so now the angular velocity is this way. Whereas before, I'm cupping around this way, going this direction. Really got that? Yeah. So that's what we call the spin around right-hand rule. So I won't write all that out because this was principle. This was on the videotape as well from last week. So, right? So the idea is if I have something that looks kind of like this, and it's spinning around like this, that's my omega. Okay. So what I'm trying to draw is a three-dimensional perspective here. Then this is going to be the direction of omega as the vector. You cup your fingers like this, you stick your thumb out like that. Has everybody got that? Okay, another example here. Suppose, okay, now I'm going to actually rotate. Okay, which way is my angular velocity going? Is it up or down? Everybody got that? No, which way is it going? All right. You can figure out how to just stick your fingers in the direction. So the second time I was going this way, cup your fingers like this, your thumb goes down. The original way was this way, cup your fingers, and stick your thumb down. Okay. Any questions? So we're going to use this spin around right hand rule to determine the direction of all rotations towards basically everything we've done with rotations is defined like this. Okay. Now the next thing we're going to talk about is kind of something cool because it's not all that intuitive. Right? Even though you probably kind of know this, it's always a little bit amazing when you see it. Right? So I've done this many times. Sometimes I actually fall off the stool. But, all right, so I'm spinning. Now I bring these spin and I go faster, and then I can slow down. And I can go faster and I can slow down. Faster. Okay? That's all angular momentum conservation. Very busy. Okay? You can try this out for class too. This is what figure skaters do. They start off with their legs and their hands far apart, and they bring them in when the city starts working fast. Okay? That's about angular momentum conservation. We'll talk about how that works. Another thing you can do is you can spin up a wheel like this. Sit on the wheel. You'll flip it over. Notice now I'm sitting instead. Okay? You can stop it. Do it there. Okay. Questions about that? Okay, so let's try to figure out how that all works. All right, so we're talking about angular momentum. Angular momentum. Okay, let's go back here. All right, first of all, we're going to talk about angular momentum for a particle. In other words, if I throw something, this particle has some angular momentum with respect to some rotation. Okay? So I'll write down let me draw the figure first. So this is the rotation axis or point. I draw it as a point, but you can think about it as an axis. And let's say we have a particle. So this is just a rotation axis. So this is an actual thing, a particle. And it has a mass m. And let's say it's moving with a velocity v. Okay. We've learned already there's something called regular momentum. And that's small p, lowercase p, is equal to m times v, mass times the velocity. For angular momentum, we're going to now talk about drawing this lever arm. This is the vector r, going from the rotation axis to where the particle is. And then the definition of angular momentum of this particle . The symbol we use for angular momentum is capital L. I'm not sure why it's capital L, but historically that's what they chose. There's an L in the word angular. That's probably how they justified using an L. And so it's R, the vector R cross the vector P. R cross the linear momentum. So this is the R you see here. This is the momentum P. Okay. Now because the momentum is equal to m times v, so this is R cross m times v. Okay. Now this m is just a multiplication by something that's not a vector. This is a number that has units, kilograms. So you can actually pull this outside. You don't have to multiply the m before you do the cross product. You can actually pull the m outside and just do r cross v and then multiply by m afterwards. It's the same answer. Everybody okay with that? Okay. Any questions? Yeah. So yeah, this is cross product. This is a cross product. These things are cross products. Of vectors. Yeah. That's a great question. If you have this particle, if it's just going in a straight line like this, it's just going like this, okay? Then what will happen, this is actually a good example of this. Remember we talked about R perpendicular? Okay, in order to calculate the cross product, you draw a line through the vector. We were talking about forces before, but now I'm drawing a line through the velocity or the momentum vector. And then you get the shortest distance between the rotation axis and that line. That's going to be R perpendicular, this guy here. And so notice that anywhere along this line, this R perpendicular will remain the same. So as a result, the angular momentum of this particle will not change depending on what it is.
And is that asking like if are we assuming it's the center of mass? Is that kind of,
Oh yeah. So it's just a particle. It's just it's just a dot. So all right. Other questions? All right. So if we're talking about the magnitude of the angular momentum, right? Then this will be the magnitude of R cross P, of course. And so that would just be R times P times the sine of the angle between them, where we have, okay, so here's, I never wrote down the angle phi here, but that would be the angle between them. Okay. Remember, P is pointing in the same direction as V, so if V is going one way, then P is going the same way. So if I have, this is my P, and this is my R, okay, phi will be the angle between the P and the R. Any questions about this? All right. Any thoughts for what the units for angular momentum is? Yes. What would be units? What would make sense as units? There's a kilograms in there somewhere, right? Yeah. So yeah, let's just work it out. Units. Okay. So we have meters for the, let's just look at this one. Meters for distance, R. Okay. Momentum, right, going back here, was mass times the velocity. So I have mass, velocity is meters per second. Okay. So the units will be kilograms times meters squared over seconds. Which is kind of a strange unit, but that's the way it works out. Questions about this? By the way, if later on you learn about quantum physics stuff, anybody heard of quantum mechanics and this sort of thing? Okay, so it turns out, this is not part of this class, that this angular momentum is actually not a continuous variable. It can't be like 3.1415965. It actually needs to be multiples of something called h bar over 2. Okay? So that angular momentum has to come in discrete packages, and the elementary particles have these discrete packages. It's really very strange. You can ask me more after class if you're interested. All right. Oh, so I should mention L is the direction of L direction is given by the right hand rule. Questions? Yeah. Okay, so what we would do is we'd say into the page. We wouldn't say negative, positive, because people would get confused which one it is. But in this, yeah, so let's just do this case. Let's say R and P are in the plane of my sheet or the screen. We do R cross, flip my, put the fingers in the direction of R, rotate my wrist so I can flick to P, stick out my thumb, so it's going out of the page. Okay, out of the screen. Okay. This is the angular momentum for a particle, so maybe I should have labeled for a point particle. Maybe I should have labeled it. I should have labeled that from the beginning. That's the simplest formula. The defining formula is actually the next one is a little bit simpler, but it's not the formula. Questions? So this is for a point particle. If you like shoot a bullet, you want to calculate how much angular momentum it has relative to some point here. And remember, the rotation axis matters. If I move the rotation axis to where the particle is, what will the angular momentum be? What do you think? Yeah, 0. So if I were to measure the angular momentum really close to the particle, the angular momentum would go to 0 because R would go to 0. Okay? Does that make sense to everybody? All right. So the point where you measure it is absolutely, the rotation axis makes a difference. Okay, now what we're going to do is talk about the angular momentum of a rigid body, rotating body. Angular momentum of a rigid body. Okay, so now we have a rigid body, okay, like this wheel. Okay. So it has a fixed axis, it's rotating. I want to know how much angular momentum it has, because if I flip it over, it would get negative with its angular momentum. And that's actually why I started spinning around, because I changed the angular momentum of this guy, and it's actually the conservation of total angular momentum that made me start to spin around. All right. So what we need now is the moment of inertia. So let's say I is the moment of inertia about the axis of rotation. So we have some fixed axis. Okay? And then let's say omega. Now we can actually use the vector hat. Before I was shy about putting vector hats because I never told you in what sense omega was a vector. But now we have this direction. Right? Remember all this spin around right hand rule stuff? Stick your fingers in the direction of the rotation, stick out your thumb. So omega is pointing like this as I change it. It's that way. Okay? So omega is the angular velocity vector. The formula for the angular momentum for this fixed axis of rotation, angular momentum of the body, it's a very simple formula. It's actually L is equal to I times omega. All right. So if you want in terms of pictures, let's make it a nice little sphere. And let's say it's spinning around like this. And the front of the sphere is going around like this, omega. Then, in terms of the angular momentum, L will be pointing in the same direction as omega, the vector, is pointing, but you multiply by a factor of I. So it's I times omega. Are there any questions about this? So this is obviously the rotation axis. Now, this formula comes about in a very simple way. We can make an analogy. So remember, when we did all these rotation stuff, I kind of beat you over the head with there's this analog between mass and moment of inertia. Do you remember? From the video? Yeah, that was from the video tape. I did that even though I didn't tell you what the heck the moment of inertia was good for. It was just the whole lecture about moment of inertia. I never really did anything. Okay, now we're doing something. So, moment of inertia is like mass, but for rotation. It's sort of how difficult it is to get something spinned up with some acceleration. The more moment of inertia something has, the harder it is to do the angular acceleration. Just like for linear motion, the heavier something is, my backpack, that means it'll be harder to accelerate. Okay? So now, so if I have the linear version analogy, I can make these connections. So this is angular momentum L. What do you think the linear analogy to angular momentum would be? Yeah, just take the word angular off. That's what you get, okay? So it'd just be regular momentum. What was the analog between moment of inertia in the linear case? What was the analog to moment of inertia in the linear case? Mass, okay? So it becomes mass. What is the analog to angular velocity in the linear case? Okay, so that's why it's very, very simple to remember this formula. You just go from Latin to well, okay, I was going to say Greek, but all these things are Latin as well, so that doesn't quite work. From P to L, from M to I, from V to omega. Okay? Make sense? Okay, now let's take the time derivative of L, okay? So let's think about taking the time derivative of I omega. Right? And let's imagine that I'm not changing the moment of inertia of this object. It's a rigid object, so I'm not doing some sort of bending of the object or anything. So then I will remain constant, and so then I have the time derivative of omega. Does anybody remember what the time derivative of omega is? Yeah, that's right. So omega is angular velocity. So if I take the time derivative of velocity, what do I get? Yeah, acceleration. So angular acceleration, right? And what is the symbol for angular acceleration? Alpha. All right. So that's why I would end up with this. Okay. Does anybody remember a formula that involves I alpha? Yeah, there was a formula. I said it was the rotational analogy to Newton's second law, right? So remember, I goes with, the analogy is M, alpha goes with A. So hopefully that formula is in your head somewhere, right? MA is equal to F net, okay? So this guy is equal to the analogy to force, which is torque. This was equal to the net torque. And so that's how I can make a connection that the time derivative, by the way, the derivations aren't that important, but I'm just trying to show you I'm not pulling these things out of thin air, okay? So if I take the time derivative of the angular momentum, I get the net torque. Okay. Is everybody following me so far? All right. So now, if the net torque is 0, in other words, tau net is equal to 0, then the time derivative of the angular momentum is 0. So if the time derivative of the angular momentum is 0, is it clear that it's not changing? It's a constant. Okay. So that means angular momentum L is constant. Okay. And so that's the principle of angular momentum conservation. That's a key concept, again, just like linear momentum conservation. So let me write this out. If the net torque tau net is 0, then the total angular momentum of the system is constant. So we would do it just like we do regular momentum conservation. We'd say L initial is equal to L final. Right? Questions about this? Okay, let's try to do an example. This is, after we do this example, we've actually covered all the material that's covered on quiz 5, so we're a little bit ahead of schedule. All right? So now, let me do this with an example. I've got it. Okay, I can do this in 3 minutes. Let's say we have a mass of 1.0 kilograms is spun in a horizontal circle with radius 0.5 meters and frequency. So remember, frequency is number of circles, cycles, or circles per time per second. Frequency of 1 revolution per second. Okay? If the string attached is pulled in, so I know it's kind of long. The new radius is 0.20 meters. What is the new frequency? Of rotation. Okay. So I'm spinning around this mass in a circle. Maybe think about it on a frictionless table. And then you can imagine even having a little hole in the table where the string is placed so that you can pull out the string from the center. Okay. So spinning around, let me draw. Okay. So it's spinning around like this. Okay, so some speed like that, some the initial, and then there's a string that goes in with some initial radius r, and then you pull, let's say there's a hole in the table, and you pull on the string to reduce the radius. And the question is how much does the frequency change? How does the frequency change? Okay, this is just angular momentum conservation. The reason there's no torque on the system, even though you're pulling on the string, you're not twisting anything. You're pulling it along the radius. So if you pull along the radius, there's no twisting. There's no twisting. Does that make sense to everybody? If you pull in the radius, R and F are opposite to each other, so the cross product, when you calculate torque, will be 0. Okay, so we're going to use angular momentum conservation. All right. Try to finish this in 2 minutes. Okay, so initially, what we have is we need to calculate, let's calculate the speed of the object. So to get the speed of the object, we know that it's 1 revolution per second, but how far does it go in 1 revolution? So the circle, it goes around a full circle, that is 2 pi ri, the initial radius, okay? So I get 2 pi initial radius is the circumference. If I multiply by the frequency, 1 inverse second, that will give me the speed. So then I multiply 2 times pi, that gives me 6.28, times the initial radius, which is 0.5, so that comes back to pi again, and then times 1, so I get 3.14 meters per second. Okay. Everybody with me so far? Okay, so now I can calculate the initial angular momentum. Uh-oh, I'm running out of time. Initial angular momentum. So that will be m times, it will be Ri times m times v. I. Okay? So everybody with me on that? Because when I do the cross product of r and v, I will get 90 degrees between the two. So there, I can put in a sign of 90 degrees, but that just equals to 1. Okay. So I have r times m times v. I plug in the numbers. Since I'm running out of time, I won't do all the details. R was 1, m times v gives me 3.14 times 0.5 for the mass. And so I get 1.57 kilograms meters squared per second. So then for the final case, I will have that L final must equal L initial from angular momentum conservation. Okay. And so that's equal to 1.57 kilogram meters squared per second. But we also know that LF must be equal to the final radius times the mass times the final velocity. Okay. So then that's equal to 1.57. So that means I can solve for the final velocity. Final velocity is 1.57 divided by the mass, which is 1.0, divided by the final radius, which is 0.20, and that comes out to 7.85 meters per second. Everybody okay with that? Okay. Angular momentum conservation tells you LF is equal to 1.57 divided by RF and M, you get VF. Now we just get the frequency, final frequency. So this will be VF divided by the circumference of the new circle. Okay, so VF divided by 2 pi R final, and you plug in the numbers 7.85 divided by 2 pi times the new radius is 0.2, and that comes out to 6.25 revolutions per second. Questions about this? I know I had to speed that up. Sorry, I ran over a little bit. I'll see you guys.